In this talk, I will show you how to unleash the potential of SmartNIC to deliver high-performance packet processing when you program them in P4. SmartNICs are increasingly deployed in today's data centers with many networking functions offloaded onto them. They achieve high-performance packet processing and save end-host CPU cycles. Different types of SmartNICs are available on the market. In this work, we primarily focus on one major type of them, multi-core-based SmartNICs. One example is NVIDIA BlueField SmartNICs, also known as DPUs. BlueField is equipped with ASIC cores for high-speed packet processing and ARM CPU cores for more flexible operation. Recently, P4 is emerging as a unified programming language for SmartNICs and has been adopted by major SmartNIC vendors. NVIDIA also developed the Docker framework, which allows programming their BlueField ASIC cores using P4. Although multiple SmartNICs are flexible and have the potential to deliver high performance, they do not have strong performance guarantee. This is because multiple SmartNICs process packets in a round-2 completion manner, where a packet is steered to a core that has a full P4 program. The core will complete all these packets execution before processing the next one. So multiple SmartNICs could have different performance when having different programs and inputs. Therefore, performance optimization is necessary and critical for good performance. This requires the compiler to work harder to optimize the program. Unfortunately, today's P4 compilers haven't taken this responsibility yet. They have very limited support for performance optimization. The reason is that P4 is the language initially designed for stage-based pipeline process, where the performance is always guaranteed to be line rate if the program can fit into the pipeline's resources. So the P4 compilers focused more on optimizing the resource usage rather than the performance. But the multiple SmartNICs are on the upside, where more resources are provided, but performance could vary depending on several factors. Besides the program itself, their performance is also impacted by the traffic distribution inside the program, because traffic going through different execution paths will have different processing latency. And the table entries, which determine the matching complexity and could also impact the execution path. We call these factors runtime profiles because they are only available at runtime, which makes it hard for compile time optimization to achieve good performance improvement. To solve this problem, we believe the SmartNIC pipeline must have the ability to change its implementations accordingly. Just like a chameleon, a type of animal that can change its colors to match the surroundings, we believe the SmartNIC pipeline should be able to change its implementation to match the runtime profile. To this end, we designed pipeline in this work, a runtime profile-guided performance optimization framework for SmartNIC. Pipeline works in the following way. It provides a profiler which constantly monitors the SmartNIC pipeline and collects the runtime profile. These profiles will be fed into an optimizer, which computes new optimizations accordingly. This will generate an optimized P4 program, which can be loaded into the pipeline using native SmartNIC toolchain. Pipeline requires to update the P4 program at runtime, which is enabled by two recent trends in the SmartNIC community. First, the ASIC cores are becoming runtime programmable, which can support live upgrades without downtime. Our NCR paper last year designed this type of hardware, and we presented it at HotChicks last month as well. Second, leading by Microsoft, SmartNICs are being deployed in a disaggregated manner, where traffic can be offloaded to neighboring NICs when upgrading one NIC. We solved two research questions in this work. The first question is how to optimize the SmartNIC program performance written in P4. To solve this problem, we first understand the P4 performance characteristics of SmartNICs by building a cost model. To the best of our knowledge, this represents the first study that relates P4 program structures to their performance profiles. The cost model inspires us to develop a set of performance techniques, optimization techniques, which transform the P4 program into more efficient implementation. Given these available techniques, the next question is how could we efficiently find the best way to use them to achieve the best performance? Naively searching over the whole program will lead to unacceptable time. We solve this problem by partitioning a P4 program into pipelines and pinpointing the program bottlenecks using runtime profiles. This approach significantly reduces the searching time while achieving great performance improvement. Let me first give you two examples of the optimization techniques in pipeline. One technique is table caching, which allows skipping complex table matches using the cache build-out. The other one is table merging, which supports merging smaller tables into a bigger one to perform the processing together to save memory access. You may hear about some of the techniques more or less from other work, but pipeline customized them for SmartNIC performance optimization. For example, traditional flow caches use only one cache for the entire program, which could have the cache entry cross-product problem, which can lead to low cache hit rate. Pipeline supports more flexible caching strategy, where we can use multiple and smaller caches. The system will automatically choose the best caching strategy. For table merging, pipeline distinguish different types of tables to maximize the performance benefit. Please see more optimizations and their details in our paper. Different techniques could result in different performance benefits, and at the same time, they incur resources overhead. So the next question is how should we choose the optimization techniques to maximize the performance benefits within the resource constraint? Naively searching over the whole program exhaustively will lead to a huge search space, because each table can take different optimization techniques, and we also need to consider the combinations between them. For example, a program with 10 tables, only considering whether to have an individual cache for each table, will produce 2 to the n cases, let alone considering other techniques and their combination. Our insight to solve this problem is that code pieces do not contribute the persistent latency equally. Some code pieces are the main bottleneck, so we could prioritize optimizing them, which tend to have more performance benefits. Inspired by the region-based optimization, we partition a P4 program into pipelines. Each of them is a 3-line P4 codelet. After that, we rely on runtime profiling and our cost model to compute the latency of each pipeline. This way, we can select the top key pipelines that contribute the most persistent latency for optimization. We then use a searching algorithm to find the best strategy for these top key pipelines. We evaluate pipeline on Bluefield 2 and the national SmartNICs. Here I show you some evaluation highlights. Our benchmark demonstrates significant improvements generated by the optimization techniques. For example, the table merging benchmark shows up to 2.1 benefits on both Bluefield 2 and the national. Our end-to-end evaluation on Bluefield 2 shows that pipeline can quickly capture profile changes and readjust the pipeline to achieve better performance. Besides, the top 20% pipeline-based search can achieve more than 17% of the performance gain found by exhaustive search, while reducing the searching time by 8.2 times. In summary, multi-core SmartNICs lack performance guarantee, and these P4 compilers have very limited support for performance optimization. We develop a pipeline in this work, an automatic performance optimization framework for multi-core SmartNICs. Pipeline has a set of customized P4 performance optimization techniques and can adapt to profile changes at runtime. Our evaluation shows remarkable performance improvements. We have more work on runtime programmable infrastructures You can find more details on my personal website. With that, I will conclude my talk. Thank you.